Until now, we spoke about how multiplexing, demultiplexing happens in TCP and UDP, but we never really spoke about those protocols. We'll now start diving into them, and we'll start with the simpler protocol, UDP, User Datagram Protocol, which is defined in RFC 768. Everybody is welcome to look there if they're more interested in the details. Now, this protocol is a best effort protocol, which means that it doesn't promise anything, and it can lose the segments or bring them to the app in the wrong order. Now, no connection is required before starting to send the data. There is no handshake, unlike TCP, which we'll see in a minute. Now, each UDP segment is actually processed separately from other segments. You've already seen the DNS, that is, Application Layer Service, using UDP as its transportation infrastructure. Another example is an HTTP/3 service, that is using multiple streams of UDP protocol instead of a traditional and reliable TCP. The reliability is achieved by defining another protocol called QUIC, QUIC, that takes care of the reliability aspects of the connection in the application layer, but manages a connection in a UDP-like way in the transportation layer. Once we are requested to add more functionality, it can be done in the application layer that is much easier for the application developers. You might ask, why does UDP exist? Because it's very simple. And we said that at least we need something to demultiplex a process correctly. But note that UDP doesn't require establishing a connection. As we already said, it has advantages and disadvantages. So what are the advantages? We don't waste time connecting. We can just send the maximum as much as we want, because there is no congestion control. Now, it's very simple. There is no connection data from the receiver or the sender. Now, in terms of the header size in UDP, it's small. Note that it includes only the source port and the destination port, and the length of the UDP segment in bytes and the checksum. That's it. Let's say a few words on the UDP checksum. The purpose is to discover reversed bytes in the UDP segment. However, even using a checksum, it is possible to miss errors. Nevertheless, this is a very simple method, which allows, in specific cases, to discover reversed bytes. So what happens to the sender? We look at all the segment data with 16-bit numbers and calculate the checksum, and enter the calculated field in the UDP checksum header. We talked a moment ago about where it is. The receiver calculated the checksum from the received segment. And if the checksum is equal to the calculated checksum, there are no errors. Otherwise, it discovers the error and the segment is then thrown out. Now, as we said, it's still possible to miss errors with checksum and transfer bad segments that were damaged in the transfer. Let's look at a case where the checksum is calculated for two 16-byte long numbers. We just simply sum the two numbers by bytes, and again sum the carry bit that was created as a result. And that is the sum we get. And from the sum, we get the checksum.